Okay, it's my pleasure to introduce Zhang, who's a faculty member in the Department of Management Information Systems at Temple University. His primary research interests are social network analysis and business analytics, and works on new algorithms and statistical models to analyze large-scale social networks, studying their applications in technology diffusion and social media. He's played key roles in research projects for NASA as well as other organizations.
Thanks for the introduction from Henry. Uh, Thanks a lot for inviting me. It's a great opportunity to share my research and at the same time get some good feedback. So today I want to talk about the research I've been working on about comparing network influence on individuals' behavior, such as technology adoption, and within the context of the ringtone purchase in the cell phone network. And because the data at my hands is very large, I would also introduce some method and models I use to analyze this data. And this is the joint work with my colleague Paul and also two researchers at Carnegie Mellon, Krishnan and David. So here's the big picture. Technology diffusion or adoption is a very popular field in information systems. At the earlier times, people believed that the reason why individuals adopt a technology, for example, I buy an iPhone, is affected by their personal attributes. For example, age, gender, income, education. So if I buy an iPhone, it's because I have high education or I have high income, etc. Eventually, people realize actually those decisions might also be influenced by people who are neighbors in your social networks. And here is an example. So here is an observed social networks, and there are two early adopters, A and B. For example, they bought an iPhone, and eventually they influenced their neighbor 1 to also buy an iPhone. And then 1 would influence his or her neighbors, such as 2 and 4, to buy an iPhone. And then eventually more and more people adopt iPhone. So this is an example about, say, diffusion of iPhone in social networks. Now, with the capability of observing multiple networks, thanks for online social media, data collections, cloud computings, we now can observe multiple networks for the same group of people. Such as if you go to Facebook, Facebook would ask you, how do you know such person? So it's possible for us to identify multiple networks for the same group of individuals. And here is an example. For this group of individuals, actually they're embedded in two overlapped networks. One is friends, the other is colleagues. So there are two early adopters in this network, 8 and 1. And eventually we observe node 3 also adopt. But because these two networks are overlapped, so it's impossible for us to really identify which network might be the real network that has such influence. So if we could separate the connections of those two networks, for example, the first one is the friend network, and the second is the colleague network, then we will realize that 3 is not connected with 8 and 1 in the first one, but connected in the second one. So in this case, we would say the influence comes from the second network instead of the first one. So this is an example about how to compare influence coming from two networks. However, the network I want to compare is not defined by social relationships. So the earlier example I show you, those connections for the social networks are defined by social relations. Instead, I'm interested in connections that is defined by network theory. So currently, there are two theories to explain adoption. The first one, and probably everyone that here know of, is cohesion. So in the cohesion theory, an individual's adoption is influenced by his or her intermediate neighbor in the social network. While there is another one, structural equivalence. In the structural equivalence model, a focal person's adoption is not directly influenced by the neighbor, but coming from those people who are indirectly connected, but they share the same social positions. So here is an example. In the picture at the left, it's the cohesion model. Assume that I am this actor. I have a friend A who just bought an iPhone, so I could be informed, suggested, or persuaded by the friends. He told me iPhone is so useful, a lot of apps, and it looks very cool, even you just hold it. So eventually, I adopt iPhone. So this is cohesion. While in the structural equivalence model, once again, I am this actor. So there is another person, C, who is an adopter of iPhone, but I do not know C. Instead, we share the same common friends, A. So in this case, I am I'm structural equivalent with C. So A told me that C just bought an iPhone. It's so cool. And after I heard this, I feel that I do not want to be left out. I also want to have the same image as C, so I feel the competition from C, and eventually I would also adopt. Okay. So comparing those two models is important because they represent two totally different target schemes. If cohesion is the real force-driven adoption, then we want to target those people such as A in the network, so eventually he will influence many friends eventually to adopt. However, if structural equivalence is the force-driven adoption, then we should target a person like C because he has a lot of people that share the same social positions, so more adoptions will be triggered by effects such as competition. So here is my context. The phenomenon I'm interested in is caller ringback tone. So caller ringback tone is a technology when you call a friend through a cell phone, instead of hearing a plain ringtone, you hear either a song or a joke. And currently, it is very popular. It is one of the most popular downloadable content on the mobile platform, and the penetration rate is even higher in Asia and Africa. For example, 95% of online music download in Indonesia comes from caller ringback tone. I hope the video works, and I have an example for caller ringback tone. Oh, the audio doesn't work. I did. Yeah. I did. Okay.
Is there?
Yeah.
It's still playing.
Yeah, that's fine. I could just explain what just happened. So the young lady at the end enjoyed the caller ringback tone so much, and she said, "Why did you pick up the phone?" So again, it means that people are very interested in such product. And here is the data at my hand. I have a cell phone phone call record coming from one of the largest service provider in the Asian country. I have both their phone call record and the caller ringback tone purchase record in the same time period, in a 3-month span. So I restrict the phone call to reciprocal, so it indicates a stronger tie. So social influence is more likely to happen. That ends up with a network with a node size of 1.4 million and edge size at 12 million. Okay, so the data is very large. So having data at this large comes several challenges. The first and probably the more important is statistics. So in a very large population, it is very likely that we have many subsets. And as the size of population increases, the heterogeneity across those sets also increase. For example, here is a network consists of about 10,000 people. And as we can see, likely there are two subsets included. So I use different color to represent them. One is blue, the other is red. And then here is an example of a network consists of 20,000 people. As you can see, as the population increases, more subsets exist. And so I colored them. Seems like there are about 4 or 5 subsets exist. And we know social norms in different groups are quite different. One good example would be, in the world, different part of the world, the culture is so different. So even I have the computing power to analyze this data set, what I would get would be an average across all these different groups. So I lose the power of identifying distinct characteristics among those different groups. Second, obviously, challenge would come from the computation cost. So for example, an MLE solution for a model likely will be used by me. Dorian's two-network regime autocorrelation model will take half an hour to analyze when the network has a size of about 1,000. And the running time would increase exponentially when the network increases. And by the way, this is the network. This is a model likely will be used by me. In this model, Y is the vector of observed outcome of all these individuals in the network. X is the matrix of attributes, covariates. Beta are correspondent coefficient. So W1 would be the structure of the first network, say adjacency matrix of cohesion. And Y is the autocorrelated term also at the right-hand side. So rho 1 is the correspondent coefficient for W1Y. Likewise, W2 represents the structure of the second network I want to compare. Rho 2 is the correspondent coefficient for W2Y. However, I cannot just directly use this model because I'm interested in a binary outcome, which is by CRBT or not, while this model only supports a continuous dependent variable. So that's going to be another challenge. So given the large data, what I want to do, instead of analyzing the whole population, I want to extract all these subgroups one by one. And I'm going to analyze them, multiple of them, and then finally apply meta-analysis to summarize all these parameters estimated from those sets. So the subset I favor are first, not very large. For example, less than 1,000. So the analysis could be done in a reasonable amount of time. And the second, I hope there are high indensities within those groups, so social influence are more likely to happen. Third, I do not want to have indense connections between this group, from within the group to the external network, because I do not want boundary leakage to contaminate the influence within the group. So talking about subpopulation extraction in the social network, so here are some commonly used methods. The first one, probably the one used the most, is a snowball. But the disadvantage of such method is, first, there's no well-defined boundary. You do not know where to stop. Or second, if you do not start from a dense area of your network, you're very likely to end up with a very sparse network. The other two methods comes from community detection. The modularity spectral optimization may be the most popular. The downside is it will take a very long time to analyze network beyond, say, millions. And the third one, greedy maximization of local modularity by Close, the quality of returned subset has never been set up. So it's very hard to find an algorithm with an ideal combination of performance and the quality of subpopulation extracted, so I designed my own algorithm. It's called transitive clustering and pruning, TCLAP. So TCLAP consists of two steps, clustering and pruning. Here is the objective function of the algorithm. So in general, what happens is, starting from a random seed of a network, I extract a subset under a predefined threshold, and with the object as maximizing a ratio, a measure called IE ratio, also defined by myself. And as you can see, so K sub S super int represents the total internal degree of a subset. Likewise, K sub S super ext represents the total external degree of a subset. So in general, this is a standardized measure, represents the difference between the internal degrees of a subset and the external degrees. Here is an example. Assume that the network included in the dashed box is the subset returned by the algorithm. And the total internal degree is 1, 2, 3, 4. And there is no interconnections between the returned subset and the external network. In this case, IE ratio is 0. Next example, once again, the network in the dashed box represents the returned subset, and there is 0 internal degree, while 1, 2, 3, 4, 5 external degree. So in this case, the IE ratio is -1. In the third example, internal degree is 4. Also, the external degree is 4 for this subset. So the IE ratio for this returned subset is at 0. So as you probably already figured out, this is a standard ratio changing from -1 to +1, where -1 represents all the edges in the subset are external edges, while 1 represents all the edges in the networks are internal edges, and there is no external edges. So my objective would be, I want to all these subsets to have an IE ratio beyond 0. So here is an example about how it works. So this is a network consists of 100 nodes, randomly generated, and I planted a denser area in this network represented by those orange nodes. So I randomly start from the network represented by this green node, and I use a revised snowball principle, which is very similar to breadth first search. So I got all the neighbors of the nodes and the neighbors of neighbors, etc., until a predefined threshold is reached. So in this case, the predefined threshold is 5. So 1, 2, 3, 4, 5. The nodes at the stopping rule has a distance of 2 from the seed. So I complete this network and continue to include all these nodes that have the distance of 2 from the seed. And that ends up with our new snowball. and I define this set as core. So eventually, this is going to be the core of my future subpopulation extracted. Then within this core, I identify the nodes with the highest degree. And then starting from that nodes, I get the next node that is connected with this node, but they share the most common friends. And then this subset of nodes is defined as the new seed set. So, and then I use this new seed set and restart snowball. So this is the snowball in the second iteration. And the same, I identify those nodes that are commonly connected and also share the most number of friends. So in the second iteration, those two nodes are the highest degree, and also they are connected. The length, the width of the line between those two nodes represent the number of edges. The number of common friends they share. So I just use this principle, restart snowball until the seed set converges. So meaning that they do not change anymore, and that gives me my final snowball. And then I will move on to the pruning stage. Okay. And in the pruning stage, I remove all these nodes that has more connections to the external network than to the internal network until the IE ratio is maximized. So this is the subset I got after the pruning stage, which is exactly the same as what I planted at the beginning. So here is an example about how it works in the real data set. So the first picture represents how I start with a snowball, and then the second picture describes the network I have after pruning. As you can see, I have a much denser network, but at the same time, I probably also include some other subset not belonging to my internal network. And the picture at the right side represents the final subset I got, represented by this orange node. So blue nodes represent another networks. I'm going to skip these slides. In general, I compared the performance of my algorithm with other two methods, Newman's modularity spectral optimization and Clauset's algorithm. And as you can see, my algorithm dominant in both the running time and also the quality of subpopulation returned measured by IE ratio. So as I mentioned earlier, there is no existing model to compare multiple networks on binary outcomes. So I developed my own model, which is called the multiple network auto-probit model. In this model, again, this is the matrix notation. Y represents the vector of outcomes, which is a binary value. It is an indicator function of a latent preference Z. If Z is higher than 0, it means customer would buy. If it's less than 0, otherwise. So Z can be represented by the sum of observed covariates X beta and the unobserved preference, also interdependent among all these people who are connected in the network, zeta. So zeta is the sum of the term W zeta. So each W would represent one network structure I'm interested in. And the zeta is also autocorrelated at the right-hand side. So theoretically, my model supports unlimited number of network. In this study, I only need two, W1 zeta and W2 zeta, where they represent cohesion and the structural equivalence respectively. So here are my two hypotheses. The first one is based on the literature. A focal person's probability of purchase CRBT is positively correlated with the number of adopters among his neighbor. And the second, the probability of a focal person's purchase CRBT is also positively correlated with all these people who are structurally equivalent in the network. So what I do is I use my TCLAP algorithm to repetitively extract many subpopulations. So I extract 100. Interestingly, I found no matter what threshold I set, I always got subpopulation falls in just two groups. One is close to 200, the other is close to 500. So this result actually also suggests the social network size in a cell phone network is larger than Dunbar's number, where it is about 100 to 230. It represents the upper limit of number of friends that we can handle in our social networks. So I just pick random 5 subpopulations from the group of 200 and another 5 from the group of 500, and then I use MNAP model to analyze them, and here is the result. In this table, this is from the group of 200. As you can see, cohesion effect is significant and positive. This is not surprising. It means more friends in my network adopt, then the chance that I would also adopt increases. Interestingly, structural equivalence has a negative and significant effect. It means for those people who are structurally equivalent to me, if they buy CRBT, then I would not buy. So it represents people want to differentiate themselves in a relatively smaller network. So here is the result for the group of 500. Same thing for cohesion, but structural equivalence becomes positive and significant. So it means when we are in a larger network, then once again, we want to be the same as the people who are in the same social position as us. So then I use meta-analysis to summarize all these effects in 2 different groups. The first one is for cohesion in the group of 200, and it has a summarized effect at about 0.063. And this one is for the group at 500 for the same effect. And the effect size is smaller. I also want to point out, because the confidence interval of those 2 parameters is overlapped, so this is inconclusive. So what I want to do next is extract more subpopulations and then do our t-test. This is the meta-analysis for structural equivalence for the group of 200. As you can see, it has a summarized significant effect at the size of 0.0067. And then for the group at the size of 500, it is positive. All right, so it is indeed at different signs. So this also indicates without MNAP model, it's impossible to identify 2 network effects. Both are significant and at 2 different directions. All right, so to summarize what I find, first, cohesion definitely has influence on people's adoption. It is positive. Structural equivalence also has significant impact and very likely to be ignored by many existing research. And the direction of such effect is different when the network size changes. So when we have relatively smaller network, it is negative. When we have relatively larger network, say at the size of 500, it is positive. So it represents different target scheme for network at different size. For a smaller network at about 200, we only need to concentrate for those people who have many friends, because eventually they will influence all of their friends. But in the network relatively larger, we want to not only concentrate on those people who have many friends, but also have people who have many competitive others. Okay. All right, to conclude my talk, my research is one of the very few to study multiple networks' influence on same group of individuals embedded in social networks. And I used multiple subpopulations to study very large networks. And I found in the cell phone conversation networks, only exist two groups of networks. One is at the size about 200, the other is at the size of about 500. And finally, MNAP model can help me to identify significant network influence coming from multiple networks. So I have to stop at here and receive some questions. Thanks.
So I have one question. So
Yes.
it looked like the structural effect in any case was much smaller, like a couple orders of magnitude. Is that, or an order of magnitude?
Oh, yes, that's right. Very good question. It is very hard to set up a direct comparison between those magnitudes because they are not exogenous. But in general, they would represent an unit increase in terms of structure equivalent, how much more the percentage of increase in the probability of adoption. Yes.